Welcome everyone! Today we are doing URL Shortener system design, one of the easiest system design problems you might be asked during interview. And that said, I saw so many incorrect solutions to this problem that I cannot stay silent any longer. So today we are building the correct, proper URL shortener together. Let's go! And as always, we are starting with functional and non-functional requirements that you should clarify during your interview. So the first one, user should be able to create short URL based or from his/her long URL. What it means is that I as a user might go and take some link from the YouTube that points to my video, go to my system and create short URL that will be pointing to my long URL. From the other side of the system, we have users that are getting redirected to my long URL from my short URL. So these two are basic requirements. There is one more kind of core requirement or something, or maybe even constraint, that a short URL cannot point to two different long URLs, because then we don't know where to redirect, right? It should be one-to-one mapping, or at least many-to-one mapping, but not one-to-many. So there is only one long URL for short URL. So it means that URL1 might be pointing to URL X and URL2 might be pointing to URL X. That's all right. So two short URLs might point to same long URL, but other way around it's not possible. So it cannot be possible that URL1 also points to URL Y, because then when we got request for URL1, we don't know whether we should forward it to URL Y or URL X. I think this is clear. Next up, non-functional requirements. First thing you should clarify is the load, aka RPS, traffic, MAU, DAO, whatever. Any numbers of the request that your system is going to handle. I checked the bitline numbers from the ChatGPT and it gave me something like 10 to 30 million URLs created per day, which translates to pretty small amount of requests that basically I would say one machine is able to cover. So let's multiply it by 10 and make it 300 million URLs created per day, or other like daily active users or whatever, which translates basically to 3.4K RPS, requests per second, or URLs per second created. This number is still something that can be handled by one nicely scaled Postgres instance, highly optimized and stuff like that. But let's assume that this number can even grow, so we anyway need to upscale, and I will provide a solution for scaling this right. For the read traffic, I would assume we would have much more read traffic, because I'm creating URL only once and I might post it to different social media. So this URL will be read and redirected multiple times. So let's say 10 times more, which would be 3 billion reads per day, which translates to 34K RPS. This is our read traffic. Let me do maybe writes. Nice. Apart from operations load, so number of operations, we also have some memory cap. So let's say we want to be operational for 20 years. So for 20 years, we should be able to issue 300 million new URLs per day, plus minus, which will translate to 2 trillion of URLs overall for these 20 years. Next very important point is cap theorem. So what should we basically prioritize? Highly available system or highly consistent system? And in this case, I would assume, and this is something you should clarify with your interviewer, that we shouldn't be linearizable, aka strong consistent, because yeah, after creating my URL, it might take some time it to be propagated and to be kind of read for all possible readers around the globe, maybe minutes, maybe even hours. I think this should be fine, and we would tolerate it in favor of highly available system. So I would say we should be eventually consistent in terms of consistency. and therefore highly available, which should be pretty much achievable. One more thing here in CAP theorem, if we choose eventual consistency, would be whether we afford data loss or no, because usually there might be a problem. If you put leader follower async replication, you might lose the data, and this should be something that is clarified with interviewer, and we will discuss it later. The last point here in non-functional requirements is the traffic type, and I would say it's spiky, aka we have celebrity problem here. Why? Because some celebrity might post our short URL on social media, and let's say the post on Twitter with our link got 1 million reads. Let's say 20% would just come and click on this link, and we will have 200k reads exactly at the same time. So we should be able to handle this as well. I would actually begin with URL lengths, or rather this path lengths, because we would have something like https short url.com, and this would be our short URL. For simplicity, we would call this exact path as a short URL. So how long this short URL should be? We already agreed here that we might have 2 trillion of the URLs, so we should support 2 trillion unique values. What are characters are allowed in this case? Well, since we are dealing with URLs, for sure we cannot include special characters like this, because this is URL parameter, this because this is URL parameter, this because this is URL parameter, and stuff like that. So we can start with 26 English letters plus 26 large English letters, uppercase, and 10 numbers or 10 digits. Altogether, they would give you 62 characters to choose from. Now, having 62 characters, we need to decide which length of short URL part we want to have, because it should be as short as possible, but still long enough to handle 2 trillion values. We can use math, try different lengths of the short URL, and see how many values it can handle. So let's assume I want 6 lengths short URL string. It will give me 56 million of values, which is definitely less than 2 trillions. Let's increase by 1. And in this case, yeah, this is pretty large number. And with having 7 characters, the total number of URLs that can be created, the unique ones, is 3 trillions, which is definitely more than 2 trillions, and we're good to go with this number. So we would say we need 62 to the power of 7 characters, so it means just 7 characters in short URL, and this is something that should be enough for our requirements. Now, having these 7 characters, we should think about the way how we can generate globally unique short URL every single time we create it. First option would be direct long URL usage, which means we can directly convert a long URL to base 62, and it will give us a short URL. There are a couple of problems. So first one, long URL might be too long, which will give us too long base 62 string, and it might be definitely more than 7 characters, which doesn't suit our requirements much. Second thing, that in this case, if 2 different users submit same long URL, they will get the same short URL, which might not be that big of a deal, but still the ideal case would be to have 2 different short URLs pointing to the same long URL. So it's basically an option that we don't go with. Second option would be to maybe use randomly generated short URL. We might just go character by character and try to get a random value among these 62 characters on each of the 7 positions, and that's how we get the resulting string. There is only one problem with this approach, because otherwise it's pretty great. We don't need to encode, transform value, stuff like that. It's random by default because it's random. But this way might generate collisions, or basically the duplicates. Let's say you even introduce some unique constraint to database, so you will detect it on insert. But what you would do with this? You can regenerate, okay, but what if second one also failed on the unique constraint. Third one also failed. How many retries you would do? How much time it will take to do these retries, right? It is user experience, it's latency. Also, what if, I don't know, 5 or 10 of them failed with unique constraint? Like, would you return to the user at some point that it is timed out, it is failed, should user retry? And bunch of other problems that we will have in case we go with this way. So I would not go with it because there are much better solutions there. Coming back to our long URL, the problem is it can be too long. It's not acceptable for our short URL. So instead of this, we might do the following. We might generate a hash from this long URL, and then on top of that, convert it to base62 value. And it will give us, depending on the hash function, I would say 256 bits of value or something like that. So this value still will be pretty long. It will not fit in our 7 characters. This is the first problem. So most probably we would need to trim it, and trimming means we might have duplicates. And here we go. We are back to our problem that we had on second option. On top of that, even if we don't have to trim, and let's say we have some magical hash function that would generate exactly 7 characters of the hash functions still might produce collision. And this is again a duplicates problem. So definitely not a choice we would do. The one might say that we can use universally unique identifiers, aka GUIDs. And my answer to this would be this is a very great choice. This is pretty good choice because practically it's impossible to make 2 GUIDs equal. However, the problem is that even if we remove the dashes, the length of the GUID is 22 characters. And we have multiple options to deal with that. Let's say we choose the easiest one to trim and take first 8 characters. We're again with the same problem, it can generate duplicates. In case we're allowed to have 22 characters as a short URL pass parameter, it would be the greatest choice here. I would go with this definitely. It seems like there is no good solution, right? It seems like no matter what we choose, we always would need to somehow trim the value, and in that case, we would need to deal with duplicates. But my answer would be there is a 5th option, which is to use unique number. What this solution is about. So basically, you might generate a unique sequence of the numbers. Let's say, for simplicity, it is primary auto-increment ID in SQL database or something like that. So we have a sequence starting from 1 and going to some maximum value. How big this value should be? Well, generally it should be 2 trillions, because this is exactly the number of unique URLs we want to be able to create. If you try to calculate how many bits this number would have, you will end up with 2 to the power of 42 number, which would be 4 trillions already. And this is more than enough. How it would look like from the code perspective? Well, we will just get a unique number. We will scramble it, which means deterministically to shuffle some bits here and there, because there will be a problem when we just begin our sequence with 1, 2, 3, 4, because base 62 from these numbers will be just a couple of characters or even 1 character, and this is not something we want to have. So in general, we will get this unique ID, we will scramble it, and then we will convert it or encode it to base 62. And conversion it to base 62 will give us exactly 7 characters max. So this is the best solution here, and this is the solution we will go with. Time to draw some rectangles. So we are satisfying functional requirements and having in mind that we have a couple of users and a couple of machines, so we don't have to deal with non-functional requirements just yet. And let's begin. We have to create 2 endpoints, one for creating the short URL, second one to resolve a short URL. So let's say there is a user, and let's say we would go with REST API, so basic HTTP. We would have post endpoint for creating of the URL. It will return short URL in the result, basically. And there is a get endpoint, which would consume a short URL as a pass parameter, and it will be resolved into 301 redirected long URL, something like this. This is how it should work on pure HTTP. As we already mentioned, we would need some unique number generator. We might use primary auto increment for that, just single table that each new record will be inserted, will generate a new incremented ID, and this ID we will use for number generation. Second option would be some Redis counter. Since it's single-threaded, it is atomic, you can always ensure the number will be unique. Just make it to sync the changes into the file on every single operation, otherwise you might lose your data. So let's say I'm drawing this, I don't know, storage. API call would go to database, get the next unique ID, and then having this next unique ID, API will generate base62 value for that, and we will store the mapping short URL to long URL in our, I don't know, URL mapping database, whatever we call it. For now, the technology doesn't really matter. It can be SQL database. In this case, maybe it is a great idea to put some index for performance. It can be Redis. It can be NoSQL, whatever you choose. So far, for a couple of users, it will work. And that's the main idea of our functional requirements. Now, having this simple architecture that will handle a couple of maybe hundreds of users, let's move to our non-functional requirements and try to satisfy them as well. So first of all, we have high load. 300 million writes and 3 billion reads is not something that this system with single machine or even 3 machines as showed here can handle. So let's scale it individually. First of all, how do we scale the API? API is stateless. It means we can spawn new instances and drop new instances without any problem, without causing any damage to our correctness. So these guys are scaled by just adding multiple instances and adding a bunch of load balancers to round robin between the instances. Good. Now we can basically infinitely scale our computes. There will be no problem. Second scaling point here is the unique ID generator. I would say that nicely optimized and vertically scaled Postgres instance can handle 3.4K requests per second. It can do that. But what if interviewer goes even deeper and says that we might have even higher spikes? Let's say on spikes we might have 10K, 20K, whatever. How would you scale this? And this is where I'm not happy most probably with any possible solution on the internet to this problem, like how to scale unique ID generator. This is pretty much the separate system design problem, the unique, scalable and distributed unique ID generator. But simply saying, what are your options? General approach for scaling would be to apply sharding. But if we shard even into 2 instances, primary ID would be the same. So this guy generates 1, 2, 3, 4, and so on. And this guy generates exactly the same 1, 2, 3, 4. So these are not unique. What are the options that people suggest is, let's say this guy can return only odd numbers and this guy can return only even numbers. This will work, but you should do very careful capacity planning because this is not scalable and flexible approach at all. Literally, you have no way to add new instance or to remove some instance from this setup because these guys, they are already pre-set up to handle only odd numbers. So if you add new instance, there is no way it can be added at all. Another option here would be to split them by ranges. So let's say this guy is handling from 1 to 101. This guy is handling from 102 to 201, and so on. This way it might work, but then you would need to be careful when your range is done. So let's say I'm 101 at that point. I need to be very careful to introduce the next range for this database. And in order for me to introduce this range, I need to know the current range of all databases. So it means I can put here from 4302 to 303, because I know that the maximum one here is 301, right? But if I don't have access to this database, let's say it's down, I cannot scale. So if this database is down, if any of the instances I have, any shards is down, I cannot introduce new shard. And this is very bad in our case. One of the pretty solid scaling approach here would be to introduce prefix ID, so-called. So basically you can assign a unique ID to each of the shards. So let's say this shard is 1, this is 2, this is 3. You just know this information either on your API configuration or inside your database itself, doesn't matter. Now each of these databases is producing exactly the same sequence. But when the sequence is outputted, you add a prefix before your generated sequence. So in this case, it will be something like that. So this instance will generate 1, 1, 1, 2, 1, 3. This instance will generate 2, 1, 2, 2, 2, 3, and so on. This is pretty good way to go, I would say. It's pretty scalable, and it would operate well. But there is even better approach, actually. There is even better approach, and this approach called Snowflake ID. So it is something that universal unique identifier was using in first versions. So you have a 64-bit number. You split these bits into 3 parts. So first one is the time span, which is a number of milliseconds starting from some epoch, let's say 1970 as a Unix time. Second part of this number is the machine ID. So basically, instead of databases, so they're going to have machine ID pretty much same as prefixes in our storages. And the third value would be a sequence number per machine ID. So this sequence number is needed only in the case when we got 2 same requests at the same millisecond at the same machine. In this case, both of them would generate same timestamp and same machine ID, but the sequence number, the third part, will be different because it will be atomically incremented on the compute, which is in general pretty fast operation. Why it's great? So first, we don't have to buy expensive storage for this. It's not a big deal if we lose instance. We can spawn more instances. We just need to take care about our configuration so that the machine IDs are globally unique. It is very fast, so it's faster than SQL insertion for sure. And it is faster than Redis insertion, even because for proper Redis insertion, you would call fsync to your append-only file, which will be pretty heavy operation still. There is a problem with Snowflake ID. It operates with 64 bits number, which is too large for our 7-character short URL. You can check my article, and what I came up with, that it can be shrinked to maximum 55 bits instead of 64. So instead of 64, you can use 55 bits, and it will be enough for 17 years of your service to produce a unique IDs. But 55 bits means that we're gonna have 10 lengths of our short URL. Now this is the question for interviewer. You should ask him whether this is okay or no, because Snowflake ID is generally a very nice solution. It covers a lot of problems. It's unique, it's easy, it's cheap. But the trade-off here is that you will have 3 characters more for your unique URL. Otherwise, another good approach for lengths of 7 characters would be a prefixed storages, which is still solid approach. Let's say for now that Snowflake ID is good enough for us. The last scaling part here is our URL mapping storage. For that one, the easiest and the most common pattern to scale the writes and reads as well would be sharding. So how do we shard? We can introduce multiple shards and apply shard key equal to short URL. Why short URL? Why not something else? Because short URL is going to be unique according to our requirements, and it means that having shard key or shard ID, let's do shard key equals to getting a hash of short URL mod number of instances. It will do a pretty evenly distributed load on our database, which is basically our purpose. With regards to mod operation, yeah, it's very bad for rebalancing. You cannot use mod operation. But for rebalancing, you can use consistent hashing or rendezvous hashing or even Redis hash slots approach that Redis is using for its sharding. Any of them would work nice, and you would not rehash all of the data inside your cluster. So any of these would be perfectly fine here. Okay, now that we're done with 3 billion reads, reads are not covered yet. So far we covered 300 million writes because we can infinitely shard it and rebalance. We handled 20 years of operating for our service because now we know that our data will fit here. We can also fix this problem with sharding. Let's try to solve the CAP theorem, and it will automatically solve us 3 billion reads. I will show you how. So we're eventually consistent, which means that our reads might be delayed and we might have, let's say, a repeatable read problem. We might create the URL and for some time we might not be able to be redirected from this URL. So having eventual consistency means we should have a high availability. So in that case, how do we ensure this high availability? So if one instance goes down, we don't care. API is trivially solved by replication. We can replicate it as much as we want, so API will be generally alive. Same happens with load balancers. We can just deploy a bunch of them inside our system and it will be fine if one load balancer goes down. It's not a single point of failure. Now, let's go to Snowflake IDs. Since, as I mentioned before, if it's Snowflake ID, losing one compute will not change anything. We can just spawn, I don't know, maybe 100 of them. And if we lose 2 of them, it will have still 98 instances to handle all the load. Same happens with the prefix shards. We don't have to put any replication here. Why? Because any kind of replication would not achieve anything. So let's discuss why. Let's say these are not the Snowflake computes, but these are prefixed shards, doesn't matter. So what are our options? We can put leader-follower replication. So now we should choose asynchronous or synchronous. So in case we choose asynchronous replication here, our problem is that we can lose the data. So if there is some write went here and we had, I don't know, number 3 and number 3 here, this number will be auto-incremented with, let's say, SQL primary auto-increment ID. It will become 4, but since the replication is asynchronous, we would return successful results straight away. Now let's say the leader shut down and it didn't sync the data to replica, and this replica still has 3 as our ID number. Now we spawn a leader election process. It elects this replica to be a leader, but now the next request that comes here, it will resolve next ID as 4, which we already did, and it violates our uniqueness. Another option here would be to use synchronous replication, and in that case, write is considered successful only if we sync to follower as well. So in this case, we have 3 here, 3 here. We would write 4 here, and if this leader will go down, well, we cannot get an OK result, and we will retry, and this write will not be even considered as a legit one because we didn't synchronize with follower. However, there is another problem here. We don't guarantee any high availability here. Because yes, we can lose leader and then follower will be promoted to leader and we are okay. But in case we lose follower, even though we have healthy leader, it cannot process any write because any write should be, all the writes should be acknowledged by follower, which is dead now. So this replication does not provide us with anything. So instead of replication here as a high availability mechanism, we can just spawn a lot of sharding and perform a round robin between them. So let's say we have like 100 of these shards. We just randomly choosing whenever we want to go. And even if one of them go down, we just round robin to the next one. And this would be our high availability technique here. Exactly the same thing would work with Snowflake. So if one compute is lost, we can just redirect or create the request from API to next one or to any other random API compute here. Now let's talk about the replication for URL mapping storage. This storage that will also receive writes, which is one thing to keep in mind. And there is only one question we should answer before introducing any kind of replication. And this question, whether we can lose data or not. What can happen actually here? If we introduce leader-follower replication here, this is one shard by the way. If we introduce leader-follower, we can lose data exactly the same way as I explained here. If it is asynchronous replication, yeah, we might lose data. And if this is okay for your interviewer that we might lose data in this mapping and user will just recreate the record again, that's fine. Asynchronous replication is one of the easiest to maintain and easiest to apply, so I would go with this one. If we cannot lose any data, then there is no other choice except not having a replication and be just strongly consistent without availability, which means that actually if we lose data here, if we lose leader here, it means our system is not operatable. It cannot create URLs and it cannot resolve URLs. Another option would be to use some something like consensus algorithm here, let's say RAFT, and in that case we would be able to lose some instances until we have majority, so until we have quorum. So let's say in our RAFT cluster we have 3 instances. In this case the majority would be 2 instances, and in that case we can actually afford ourselves to lose one of the instances here and just leave these 2 instances. So both of them would be a correct approaches. That's okay. Now we have everything scaled at the moment, but there is one more problem. First one, we have spike-ish load type, and second one, we still have much more reads than writes. How do we scale them? So reads are easy to scale by just doing a replication. So if we came up with RAFT or leader follower, doesn't matter, we can just spawn maybe 5 more replicas and make reads to go through all the replicas instead of leader one. In that case, we can just infinitely upscale our reads, and it will be no problem with that. With regards to spike-ish behavior and celebrity problem that we might have, well, one of the options would be to introduce caching as well. So instead of read replicas, we might have the cache either near the cold storage or near the user, so regional caching. Both of them would work depending on the trade-off. And in that case, yeah, user first go to cache, and then if user cannot find this URL in the cache, it goes to cold storage. So it will decrease the read traffic on our cold storage a lot, but it will increase traffic to cache. But still, cache, we don't care much. We can lose it. We don't care about the data. We can put just Redis as a distributed cache only in memory, and we can put bunch of the replicas of this cache as well, so we will handle any kind of celebrity problems in that case. Well, I would say that's it. That basically the system that will operate and satisfy both of our functional and non-functional requirements. Please share your thoughts about my decisions made in this system design. Maybe you have some improvements, maybe you have some other ideas. I will be happy to discuss them and to maybe redo this video if you find huge technical depth here. Also, please, you can go and read the full technical article on my blog if you want some more details. On top of that, I have POC implemented already in my GitHub. You can check the link in the description. I think that's it for today. Thank you for your attention. Please don't forget to subscribe to my social media. I'm doing lead code and system designs in my Telegram and Instagram. Links can be found in the description. It was me, Andriy, and see you.